will make some progress. So yesterday in the office hours, I was mentioning this to your friends that so far, if you are able to solve problem 1 and problem 2, excluding the challenge problems, then you are in a good shape. Okay, so you don't need to worry about it. Okay, problem 1 and problem 2, excluding the challenge. Problem 2, after the challenge part of problem 2, after today's class, you should be able to do very easily. Problem 1's challenge part, you may still need a little bit of thinking, but yeah, so, and so let's look at problem 4. In problem 4, we are so what are we supposed to do? We are supposed to compute sigma I is equal to 1 to n square root of I. This is what we have to do. That's problem 3. Yeah? Oh, problem 4 is, what are the patches? Do you still have patches on your screen, or you may have patches around, but not on the main screen, right? No patches on Essential C book, right? Okay, good. The patches are Zoom. Yeah. So anyway, so this is the problem we would like to solve. And yesterday in the session, I talked about solving co-primes problem. So this is the problem we we want to compute this expression, and but you know that square root of an integer is not an integer. It can be it can be a fractional number, a decimal number, and so the data types that we have learned so far, there is only one data type that we have learned so far. What is that data type? So we learned about the integer data type. But integer data type is not sufficient to solve this problem. So because we are working with numbers such as 10.456 or numbers where there are digits after the decimal point. And also when it comes to, so we have to use what are called as floating point numbers. We will take a look at the floating point numbers in a moment. But even when it comes to integers, I would like you to bring to your attention that most of the time integers are encoded using 32 bits or 4 bytes. 4 bytes of memory is allocated to an integer. And so when we have 4 bytes or 32 bits, and the number of integers are infinite, so you will not be able to represent all possible integers using 4 bytes. So the range of integers that you can represent is using 4 bytes is this. So why this you will understand in some time. Okay, we will take it up in a different class, but this is the range of integers that you can represent using integers. But if you use long integers on many systems, you will get 8 bytes of memory or 64 bits. So using 8 bytes, you will be able to represent integers from a wider range, from a wider interval. But if the value of an integer falls beyond this interval, then you will not be able to represent those integers. Good. So in cryptography, so usually let's say in most applications, this should be all right. But there are some specific applications, especially in cryptography for encryption, decryption algorithms. So using 128 bits, 256 bits, 512 bits, etc., is quite common in cryptography. What did I write in? There is no brackets. This one, you mean? This is an interval. This is the range of integers which you can store using int. Cryptography is where you encrypt things, secret stuff. So you will learn later. But in cryptography, this is store. It's all encoding, encrypting your secrets. When you're sending a message, you want to encrypt your things so that other people wouldn't see what you're doing. Like, for example, when you're sending your credit card information over internet, you don't want other people to know about your credit card information. So you kind of encrypt it. And so there, you require, it is very routine to work with bigger numbers. And the standard C programming language is primitive data types. These are called as primitive data types. They are not good enough. Int, short, long, so these things you have to define new data types and work with them. So let's not worry about this for the time being. I just want to bring to your attention, when you are using integers, you will be able to represent numbers, integers which fall in this range. And if you want a bigger range, you go for a long int. And beyond that, we have to use some other mechanism. And short usually gives 2 bytes. So the usual convention is short 2 bytes or 16 bits. Int is 4 bytes. And long is 8 bytes. All right. So this is about integers. And let's keep going. And are you all with me on this one, on this particular thing? Just focus on the important ideas that I am highlighting. So now let's go and see floating point numbers. So when you want to represent numbers such as some fractional numbers, then you need to use what are called as floating point data types. And there are 2 kinds of floating point data types. One is called as single precision floating point number, which is called as float, and we use 32 bits to represent. And other is double, which is 64-bit floating point number. So if you take, let's say, 2, the representation for 2 as an integer, the representation for 2.0 as a float, and the representation for 2.0 as a double, the representation is different for all these cases. Okay. Using double, you can represent a wider range of numbers, and the granularity, the precision also increases. Just assume for the time being, double is more powerful than float. Okay, double is more powerful than float. Are you all with me here? Just like, for example, using float, you can represent some range of numbers. Using double, you can represent a bigger range, and also the precision also can increase. And other important thing I want to remind is 2 plus 3, you take the same operation, 2 plus 3, and so this you do in the integer space, and this you do in the float space, in the floating point and this you do in as double. So you know that the representation for 2, as I said, it changes from as in the bit pattern. If you look at the bit pattern associated with the representation of 2, it would be different for int, float, and double. And also the other thing is, you know, like when you are performing addition, ignoring all computers, etc., the way you do arithmetic for integers is different from the way you do arithmetic for decimal numbers, right? Yes or no? Decimal numbers means that whatever that fractional things. The algorithm is different. For multiplication also, you have to be careful, you know, like how do you place the dot when you multiply two numbers? All those things will change. So because of that, so this same plus operator, it means at the processor level, the plus here and the plus here and the plus here, these are three different kinds of pluses. They invoke different kind of circuitry at the processor level. Are you with me on this one? That the plus here and there are three different pluses, and these three different pluses are different because they invoke three different circuitry at the processor level, because the algorithm for computing this addition in these three different cases is different. So, and then if you have something like 2 plus 3.0, then, so this is an integer and this is a, let's say this is a float. Then there is a problem because in the processor, it cannot add an integer to a floating point number. It's like adding apples to oranges and the processor would get into trouble. So what happens is we will look into it in a bit more detail. So we do what is called as a typecasting and then convert this 2 to 2.0 in the float format. And then we apply addition operation. Because then it's like adding apples to apples or oranges to oranges. This is typecasting. I didn't write it clearly, so typecasting. Not the computer, the programming language, your compiler does some things. We'll get into this stuff. Okay, I'll take a look at this. So this is, so in order to solve the problem, this is a summation problem. This is sigma I is equal to 1 to n square root of I. You need to know about these details. You need to know about these details. So the rules for typecasting we will study later, but let's just follow along my train of thought and see where we go. So let's say we are working with circle.c. So now we are writing a program. Let's see, include std.h. Okay, so I'm defining three variables. So the first variable is radius. The second variable is area. And the third variable is the circumference. These are the three variables. And then we have the statement, enter the radius. And in order to read a floating point number, the format specifier that we use is %f to read a floating point number. Are you with me on line 8? On line 8, are you with me that in order to read a floating point number, the format specifier we have to use is %f. Next, so area is equal to pi r square. And now I am introducing a new macro feature called as define statement 3.14. Radius, circle radius is equal to %f, area is equal to %f, circumference equal to %f /n, radius, area, circumference. Nice. Great. Okay. So there are few ideas. This program is very interesting. There are many ideas that we are introducing now. The first idea is on line number 3, we are using a define statement, and this define statement is processed by C preprocessor. This is taken care of by what is called as a C preprocessor. It's a program. What this does is, pi is not a variable. Wherever pi is present, it replaces pi with 3.14. So let's see what happens. So in order to understand, so pi is not a variable. Okay, in order to make you understand what is happening under the hood, let's go ahead and let me minimize this. Let's go ahead and the CD CP21. GCC ABS. Yeah. So circle.c, let's first see what this program does, and then I will discuss about the features of this program. GCC circle.c .a.out. Okay, and then if I enter the radius as 3, we get the radius of the circle is this, area is this, and circumference is this. And if the radius is 2.3, and this is what we get, so on and so forth. So you know how the program is working, right? Are you with me on this program? Just at a high level, what is program, what is input to this program, what is output to this program. And we can control, like for example, you can tell the program that after the decimal, I don't want 6 digits. You see there are 6 digits here, and you say I'm not interested in 6 digits, I am just interested in 3 digits. So you can say percent 0.3. Maybe you want 4 decimals after area, but for circumference, so no, not this 0. Yeah, just. So now when you compile this program, let's compile this program and see. And if we enter 2.3, now you can see that radius after decimal only 3 digits are printed, but for area 4 digits are printed for area, and for circumference 4 digits are printed. Okay, 14.444, 3 digits are. It looks like it is rounding off the digits. Okay, you have to check how it does. So line 15, you are printing radius, area, and circumference. And this is the first placeholder, this is the second placeholder, and this is the third placeholder. So this is the first placeholder, second placeholder, third placeholder. The first placeholder, second, third. So this is the mapping. Wherever no first placeholder is there, radius will go sit here. Similarly, area and circumference, no, this second and second they match, and this is matches. This is clear, right? And then dot after we put decimal 3f, meaning after the decimal point, just print 3 digits. It doesn't work, Harshit. This is not Python. Okay, so we have to have placeholders, then only it will work. Yeah, it is. Okay. So just for a change, just to illustrate a point, for area, we use .4 point, decimal point followed by 4. For radius and circumference, we asked printf to print 3 significant digits. Are you all with me on this example, line number 15? One thing at a time, guys, one thing at a time. Okay, I will explain point 3 again. I just want you to focus on the printf statement, understand it completely, and after that we go to line 3. Okay, I hope you're all good with the printf statement. Now we will move on. So as I said at the beginning of the course, now when you have a doubt, write it down on your book. Okay, if I don't answer your question by the end of the class or no, then you ask me again. Okay. Patience, because we are following a certain flow. Let's try to follow that flow. So line 15 is done. So now the bugging question, what is happening on line 3? So as I said, what happens is, so this program, when you say GCC, so what happens is your circle.c program, GCC, what it does internally is it passes your circle.c program to a program called as CPP. And then it generates internally what is called as circle.i. And then this program goes to C compiler called as CC1, and followed by that some other set of programs will be invoked. And all these things are done in the background transparently by GCC. We don't know what is happening, but GCC automatically takes care of these things. All right. So now let's see what CPP does. So let's see what CPP does and try to understand. So now CPP circle.c greater than circle.i. That means the output of circle, the output of the program CPP is redirected to another program called as circle.i. So now let's go and look at circle.i. Control F, main, yeah. So now in the main, you can see on line number 738 that the constant, the preprocessor constant pi or macro as we call it as pi is replaced with 3.14 in the area calculation. And similarly, we did the same in the circumference calculation also. So pi is not a variable, capital Pi is not a variable, it's a macro, and it got replaced, and who replaced it? The program CPP, C preprocessor replaced it. Are you with me here on this one? With variables, you can use a variable. I just use dot a meaning intermediate. So with a variable, what happens is you can change the variable. So someone can accidentally change a variable. Macro means that's what. So this pi that we defined here, it is what is called as a macro definition. That is, this gets replaced. This is a feature. But if you declare instead pi, you cannot modify pi. Like for example, in the program, when you say pi is equal to something, whatever, some value, you'll get an error. You can already see that there is an error coming. So there is a problem. So then what happens is this statement internally gets translated to something like, 3.14 is equal to 12.0, and the compiler raises an error. You'll get an error. So this is not allowed. So that is the difference between, but on the contrary, if it is int pi, it's okay. You can, if you say whatever float pi is equal to 3.14, you can change it. Okay, you can change it. And that may not be a good thing. We may accidentally change a variable, and the semantics of the program will change. So the advantage of using a macro is macro just gets replaced. Macro just gets replaced. Pi gets replaced with the value. So pi is a different name for 3.14. We don't need to use CPP explicitly. It is automatically done by GCC. We don't need to use Gaurav. So that's what we directly compiled. We used pi, but we compiled directly using GCC. Pi is replaced with 3.14. Wherever pi is there, pi got replaced with 3.14. That's what we are showing here. Pi is a different name. It's not a variable. Okay, wherever pi is there, it got replaced by 3.14. It's a placeholder for 3.14. So now, let's move on. Yeah, so what are the advantages of using pi? Let's say when you are writing a program with, let's say, some 10,000 lines of code. So if you are writing a program with 10,000 lines of code and there is a team with 10 people, if you are using pi value as 3.146 and your friend is using pi value as 22/7, whatever, then what happens is if there is a mismatch in the calculation of in the usage of the pi value, then your program may end up having bugs. Or the other way is, you are using pi in 20 different places in your program, and later on you decided, hey, I don't want 3.14, I want to use 3.1417 or something like that. And you replaced that value of earlier value of pi at some places, but you didn't do the same in some other places. So again, you get into trouble. There is this global variable can be changed, but pi cannot be changed. One has it right. Srikanth, it's a good question. You cannot, if it's a global variable, you can change the value of it. Okay, so let's not worry about global variables. So focus on what I'm telling is your You're all extremely good at trying to pull me in n number of directions, and just focus on where. What did we learn? We learned about printf, how to read floating point variables, how to read floating point variables. I want all of you to take a pause on the chat box, take a deep breath, relax. Okay, your minds are all going fast, confused, sometimes going ahead. So you should relax. And so I want you to understand the important points. Are you all with me on this first idea? Line number 7. Are you good with that? Okay, just follow my train of thinking. All your questions will be answered, if not in this lecture, in a different lecture. The second idea is scanf, that when you are reading a floating point number, that you have to use the %f format specifier. Again, are you with me here? The third idea is when you are using printf for floating point numbers, you can use this %f format specifier. That is the third idea. The fourth idea is the use of pi as a macro. So how does it work? You have alternate, why can't we use global variable, all those things, let's keep them aside. What it does is, what the C preprocessor does is, it replaces this pi with 3.14 wherever it is present. Are you with me on point 4? Okay, great. So if you are with me on these 4 points, you are doing good so far. And the next set of ideas I'm going to introduce you are important. You should pay attention. Pay attention. Pi is not a variable. It cannot be changed. Okay. Now look at statement on line 15. So this is an important thing. So area is equal to, we are writing an expression tree here, pi times radius. And here the multiplication operation, you can multiply radius times radius followed by pi, multiply it with pi, or multiply pi with radius and then whatever the result that comes, you can multiply. So 2 ways of multiplication. So pi times radius and then followed by this is one way. Other is pi times radius times radius. Both are possible. And this is the C language uses this convention, and this convention is called as left associativity. You multiply from left. You multiply from left. You multiply pi with radius. If you see this expression tree, if let's say pi is equal to 3.14 and and radius is equal to 2.0, so 3.14 times 2.0 is 6.28, and then you have this radius 2.0, and when you multiply these two, you get some value, let's say some 12. What do we get? Maybe 12.56, and this value gets copied into area. Are you with me on the expression tree? Again, getting distracted. Focus. Okay. Are you with me on the expression tree and the left associativity property? So that is the fifth idea that I would like you to understand. So idea 5 is left associativity property. And now I want to introduce one more So in left associativity, all we are doing is when we are multiplying pi times radius, you multiply pi with radius first, and whatever the value you get, you multiply it with the radius on the rightmost side. That is, multiplication is happening from left to right. That's all left associativity means. Now, line number 16 is interesting. So equal to, I just use capital C for circumference to save some screen space. Radius. So now, and pi is 3.14. So now there is a problem because you cannot multiply 2 with 3.14 because 2 is an integer and 3.14 is a floating point number. You cannot multiply apples and oranges. Okay, so they have to be the same data type. So what happens is this 2, it gets typecasted. So what happens is this 2 gets typecasted. This is the, so 2, this is what is called as, this is implicit typecasting. Yeah, this is what is called as an implicit typecasting. You typecast 2 to float. So now what happens is this is what is called as a automatic or implicit typecasting. You are not doing anything, but the compiler automatically does this for you. As a result of this implicit typecasting, so 2, when it is typecasted, the value of it becomes 2.0. The internal representation of 2.0 will be respects the floating point representation. Whereas the implicit, the representation for 2, it is an integer, it is different from 2.2. Now the multiplication that happens between 2.2 and 3.4 in the processor, it will be a floating point multiplication, F multiplication, floating point multiplication. And whatever the result that comes, it just keeps going, and finally we come all the way here. And this is the 6th idea that I would like you to remember, this idea of implicit typecasting. Are you all with me here? These are the 6. Left associativity works even for addition as well. All good? Happy so far? Point 6 is, see, integer, you cannot multiply an integer. You cannot multiply 2 times, 2 times 3.14. The processor cannot do. It cannot multiply an integer with 3.14 because there is no hardware circuitry which can multiply an integer with a floating point number. So what happens is this 2 gets converted to 2.0 floating point number. This is float and this is also float. And then it can, the process, and then this can be mapped into an instruction which the processor can execute. Are you with me here on this point? This is what the point 6. What is there in left associativity, guys? You just, when you're multiplying, you just left from left to right. No, that's all. Multiply from left to right. That's all. So when you're multiplying 2 times 3 times 6, you multiply 2 times 3 is 6, 6 times 6 is 36. That is left associativity. If it is right associative, then you do 6 times 3, 18, 18 times 2, 36. In some cases, mathematically speaking, for it should not make any difference, but when you work with floating point numbers, it will have an impact on the value that is produced. The processor doesn't do, Ramandeep, the compiler does it for us. The compiler creates an instruction for typecasting. Okay. Again, I want you to understand what I am telling you. Keep asking some questions. You will get answers to those questions. I'm not going to answer. You will get answers later. But are you with me on whatever you are seeing on the screen? All right then. So these are very important ideas. These are very, very important ideas, what you are seeing. Now, let's write one more program. So, okay, so now, so in the problem you want to find, we can't there's a problem where you are using square root and we would like to solve that problem. Okay, in order to solve that problem, so let's see. So stdio.h, void main. Okay, so printf enter n. Okay, printf square root %f is equal to %f slash n. Okay, so I know your so here, so this is a program we are where we just take an input 10 and we try to compute the square root of it and we print it onto the screen. Let's try to see and compile what happens if you try to compile this program. So if you try to compile this program, you will see, like, hey, strt warning, implicit declaration of the function strt, and then you will see one more thing, include math.h, so on and so forth. Okay, so if you do man, so sqrt, so you will see that in order to use sqrt, we need to use we need to include math.h. So we go ahead and include math.h in our program. We go ahead and include math.h. So now, yeah. So let's see. GCC sqrt.c. You will see that there is still a problem, including just math.h is not sufficient. We have to use what is called as a linker option, minus link math. Minus L stands for link. M means link to the math library. Minus LM stands for link to the math library. Okay, so this means link to the math library. math. Let's run this program and see what is going on here. So you can see that square root of, even if you enter 3 is read as a floating point number, you get this 10.11 square root of so on and so forth. So a couple of things I would like you to mention here. That is, so if you look at man SQRT, if you see what you have here is what is called as a function signature. What is a function signature? The function signature tells that SQRT retakes one parameter and the type of that parameter is double, and it returns a value and the type of that return value is also double. That's what it says. But if you see our program, we declared n and square root of n as floating point numbers. So again, what happens is, if you look at the expression tree here, so SQRTN is equal to n, and so we have to apply SQRT to n. So SQRT expects a double as an input, and but we are giving n as an parameter. N is which is of type float. So it has to be typecasted to float. So this has to be typecasted to float through implicit typecasting. So that n, it needs to be typecasted to a double, so that SQRT can read it. Okay, so what happens is, so here n, which is a floating point number, it gets promoted or typecasted to a double. And during that process, do you think there will be any loss of information? When a float gets promoted or typecasted to double, there will not be any loss of information because double has a bigger range. Okay, it's bigger, it can accommodate floats. But then if you go from SQRT to SQRT returns double, so this whatever the value which SQRT returns, it needs to be typecasted to float, because SQRT returns double, but SQRT n is float. So there is a loss of information when we are going from here to here. So there is a loss of information, And this loss could be, in some cases, it may not be a big deal, but in some cases it could be disastrous. So this could be disastrous in some cases. And so what happens is, let's say you wrote a program which helps calculate the trajectory of a rocket which is going up to some orbit, which is taking a satellite to some orbit. So it is repeatedly calculating the path, okay, trajectory, and there is this minor loss of information at every point, and this could keep on amplifying, and at some point it can go out of the trajectory and land up in ocean instead of going up and sitting in the orbit. Or you do this and the error is so small, and you are sending some mission to Mars, and it is important that you land your rover at a particular point. And if it is off by, let's say, 100 meters or 200 meters, then it will end up landing in some crater, and it is hard for the rover to come out of it. But when you send something to Mars, it will take multiple months. And these repeated calculation errors, although minor errors, they keep on accumulating, and they can spread into other computations. And finally, instead of landing at some place, you land at a place which is little bit away from that place, but that could be a bad thing for you. Okay, so you have to be careful Okay, you have to be careful. One question Suyesh asked, like, you tell me how can we avoid this in this particular case? In this particular problem, how can we solve this? Yeah, you can use double. Okay, you both of them, you declare them as double on line number 6 instead of using float on line number 6. Okay, are you with me on this example? Are you all with me on this example? Okay, good. Awesome. And now, so try it, Anika, and see what happens. Now, one important thing, again, I want you to understand here. So when we include math.h, the code for the square root function is not included, but instead a declaration about the signature of square root function will be included. So let's see. So let's go back here. Pay attention here. CPP circle sqrt.c greater than sqrt dot I. So now let's open sqrt.i. So now if you see sqrt, I'm searching for sqrt. Yeah, I want you to pay attention to line number 873. This is the place, this is a line in the math.h file which tells the signature of the sqrt function, which tells the signature. What is it telling about the signature? So how many parameters are there for sqrt? How many parameters? One parameter. What is the type of that parameter? And what is the return type of sqrt? It is double. And there is this keyword, this is observation 1, observation 2, and there is this keyword called as extern, which tells that the code for sqrt is present elsewhere. What is that elsewhere? It is the math library. Are you with me? That extern keyword tells that the code for math for sqrt is present somewhere else. And where is it? That is the math library. Similarly, if you go and look at line 870, you see this function pow. How many parameters are there for this power function? What are the types of the parameters? Both are double. And what does power compute? Power computes x power y. And what is the return type of double? It is of power, it is double. And what does extend say? That the code for POW function, it is not available here. It is available elsewhere. It is not available in not in math.h, Rohan. It is available in a math library, which is completely different. Math.h only tells the compiler what is the signature of power, sqrt or exp2, log2, all these functions that you are using. But the actual code for them is present in a separate library, and we link our program with that library. We link our program with that library using the -lm option. It is connecting the file to a lib file. Yeah, it will include, Anusha, it will include all the signatures that are present in math.h, irrespective of. So Abhinav's question, why is it not required on Windows? Maybe on Windows they are linking it with math library by default, or something else is happening. Now these are all include file, these are all lines. Like when you include math.h, you can use all these functions. Otherwise, what do you have? You will have an include file for sqrt, you will have an include file for POW, you will have an include file for log2, so on and so forth. Yes or no? That's painful, no? So you have these 500 functions, and you have some 500 functions, and all these functions signatures, they are available in one place, like a dictionary. No, so for printf, Not like for every header file, Kiran, just for math you need to use and for some other libraries. For printf and scanf, what happens is they are the standard STD, standard library, standard input output library, it is linked by default. So let's look at the signature for printf. Yeah, so clear. So you can see on line number 415, this is the signature for the printf statement. See, if you are using Linux machines, you have to link it with the math library. But on some other machines, no, the linking could be happening by default. So I don't know. Its code will be included, Anusha. When we call SQRT, its code will be included, but not at this level. See, what happens is, this is your program. So what happens, your SQRT.c, it goes through CPP. And then, so you get SQRT.I. And then let's say this goes to a compiler called as CC1. And it generates SQRT.O. And it goes to what is called as a linker program. And linker generates A.out. And what the linker does is it pulls in the math library code. Math library. And it also pulls in standard input output library. So this is default. This linkage is default and this one is explicit. We have to explicitly, and this could change from system to system. Okay, this is default, this is explicit. Linking standard library is, so when we do this linking, the code will be extracted and A.out contains the code. Are you with me on this picture? Are you all with me on this picture? So SQRT.I only contains signatures, only signatures. Only function signatures are present. No code. But here the actual code for the SQRT printf will be there. This one. Huh? So here, after this A.out contains code for SQRT, printf, everything will be there in the code for A.out. CC1 is a compiler. It is actual compiler, core compiler, which maps your C program into equivalent assembly code. Linker, the box, this is what is called as a linker program that links your program with other. CPP doesn't convert SQRT.c to executable file. It converts it into that intermediate file SQRT.I. There is no dot or extension. My handwriting is pretty bad. This is O. Yes, no, GCC is all, GCC calls CPP, it calls CC1, it calls linker, and it calls other necessary programs. It calls all of them together. .o is not an executable. GCC does all of this. Yes, that's true. Are you all with me so far? Are you with me? You understood the summary picture? So if you see, let's see, if you go to cd slash, what crashed my computer today, huh? So we are in serious business today. So no crashing. we'll do it. Yeah. So if you go to lib, yeah. So if you see, so there are lots of these libraries. If you let me clear my screen. So you can see this is a directory. I'm in this lib directory. You will see lots of libraries .so files, and these files, they contain code. When you use some special functions which are present in these libraries, you have to explicitly link your program to these libraries. So there are some other paths also. I don't exactly know where the math library is located. You should tell me, someone can tell me where math library is located. Okay, find minus. No, that's not. No, include is different. Include contains include files. Include files are different from math libraries. Include is different from math library, guys. Okay. Okay. I think it could be somewhere. Anyway, it's not that important, but see that math.h is present in include, but we are not looking for the include directory. We are looking for the place where the sqrt function is present, the file or the library which contains sqrt. Anyway, so let's take a step back. So I'll ask a series of questions and then we will conclude. So your input C program is first processed by who will process the include statements in your C program? CPP. Who calls CPP? GCC calls CPP. And so, yeah, so what happens? Let me draw this picture again for the sake of everyone. sqrt.c got transformed into sqrt.i due to the CPP program. All right. And that sqrt.i, does it contain the instructions for square root or power? Does it contain instructions? No. What does it contain? It contains function signatures. It contains function signatures. And then this sqrt.i gets converted to sqrt.o by CC1. CC1 is actual C compiler. This is the C compiler. This is a real C compiler which translates C code to machine language instructions. Are you with me here? Summarizing today's lecture, sqrt.o. So sqrt.o, does it contain instructions for your sqrt function or POW function? No. This needs to be converted to a.out Who converts it to a.out? The linker program converts it to a.out. And what does linker takes as input apart from strt.o? It takes like for example libm.a, which could be for example math library. Okay, so math library it will take, and it will also take standard input output library and any other library, standard IO library for printf, scanf, etc. And then it generates a.out. This is the picture. Are you all with me? CC1 is the one, this is the one which converts the C program to machine code. This is the core component, guys. This is everything else is, if this is not, this is the most complex part, translates C code to machine code, machine or assembly code. This is the most important thing. A.out is the executable. No? And GCC, and who does all these things for us? GCC does it for us. I want you to watch this video again and get back to me with questions on Thursday. Is it a fair thing to ask? Because we repeated these ideas multiple times in the same class. Perhaps you should think a bit on your own, watch the video slowly, do some research, reading, and then you can again ask me questions on Thursday class. No crash today. We will do it some other day. So yeah, machine code is that x86 64 or no, it's true. Quiz next week. Hey, don't worry about all those things, man. Just study, learn the ideas. You're so much worried about these quizzes and all. Okay, that's all. I'm hungry, so so we will catch up on Thursday, and the ideas required to solve other problems we will discuss. Sorry, it is already 1:15 now. We will not be able to do it. We will do it on Thursday. Okay, you should also have a fresh mind. We also discuss lots of things. But after Thursday class, you should be able to solve all the homeworks relative is. Okay, that's all for today. And I will see you on Thursday morning.